Is it okay? Okay.
All right, so our second talk for today is from Siebert from Texas, who is going to tell us about intrinsic mirror symmetry.
Yeah, so in a sense, I think, although mirror symmetry is an old subject, it's still in its infancy in terms of a mature kind of mathematical subject. Because the question that has been posed to us, or that we have asked ourselves for a long time, what is it really that mirror symmetry is talking about, has not been answered. Okay, so it's nice to play. Okay, we all love to play and have like constructions and then check and be amazed of what comes out. But to make mirror symmetry into a tool, we first need to say, here's a natural category of objects. So nothing like coming from a construction, but something that other people care about, okay? And that's what's I think we have an answer to now. So this is joint work with Mark Rose, of course, and some inputs also of our collaboration with Paul Hacking, Sean Keel, Dan Abramovich, and Chile Chen. You will see. So, I also want to say I really liked that the people who, like early on, asked the question, okay, let's use mirror symmetry as a tool, like Golishev and Alessio and also Ludmil, who asked us to apply to question algebraic geometry, and for a long time we couldn't do it. Okay, so what are the natural objects? So we have two main classes. The first is degenerations of Calabi-Yau's. Maximal degenerations. Of Calabi-Yau's or Calabi-Yau pairs. So that is a situation where you should just give yourself a family. Let me write this over a disk, but you could take a higher dimensional space. Of, let's say, proper Calabi-Yau's, compact Calabi-Yau's. And the only thing you know is that the monodromy is maximally unipotent. In maybe not the strong sense that Morrison would have defined it, but just saying you can fill in a central fiber of the base change, which is normal crossings and has one deepest point. So meaning a zero-dimensional stratum. Okay? That's the kind of generality we will produce mirrors. The second case, which one is actually a special case of with some additional structure, is just log Calabi-Yau's. And I want to take a very liberal definition. So that's a pair, x comma d. And the only thing I asked is that kx plus d is numerically equivalent to an effective divisor supported on d. So d would be the union of the di, and ai should be larger or equal 0. It's the only thing I want. Okay? And I think with this definition, then you can start playing, really, and proving we have this construction. Check how the mirror construction changes on various operations, and so on, and so on, and so on, right? Okay, so this is the theorem I'm promising. That's a logarithmic, that's a class of the logarithmic tangent bundle. So the easiest, no, otherwise it goes -1, right? Well, you could write kx sum a and then a larger or equal -1, okay?
And ai can be rational?
It can be rational. It can be rational.
So a general type quantity that the economic divisor is log Calabi-Yau?
That general type, no, it's minus kx would be You wouldn't, no, that wouldn't work, right? Then Kx doesn't have a section. Sorry, Kx has a section, but it's not numerical to a divisor. Well, you could take, no, you can do that too. Right, so another case is, maybe I put this here as 3, although I wanted to put it as a remark. We can also do the case where you just ask C1x either nef or anti-nef. So maybe that also answers your question. So the result is announced in 2016. It's on the archive, and we hope to put out the paper that's lying on my desk here this year. Stays of revision. Okay, so the result is construct mirror family in all these cases, mirror degeneration. In both cases, in all cases. Yeah, via some version of log chromophyton theory on x, d. You will notice that it doesn't depend on how you choose your model so much in this formulation. So I will assume that x is smooth and d is normal crossings. Okay, so in one parameter degeneration, you can always assume that. Simple normal crossings. Once we want to put this, of course, then the whole thing, it's like part of some program where we, of course, have to connect it with our previous constructions using wall structures. This thing will not involve wall structures explicitly. Okay, we are building the ring right away, and then we have to show that we want to show, and sure we can show it, that it's we can also get a wall structure like we did in the theta functions paper. So we'll get everything.
I'm really confused. So if I take x to be like a higher genus curve,
Yeah.
and d a point,
Yeah.
then what chromophyton invariance are you?
Well, in this case, it's presumably trivial what I'm getting. Okay.
But there's a mirror.
There is a mirror, but it will just be boring, I guess. Let's continue. And then afterwards we can. I mean, it's a construction, right? It's a theorem, and then you can ask all cases, and it will not always be trivial to compute. Okay. So I'll do the following running example. Let's see. Did I miss anything? Right. So I will focus on that case here. Let's forget all the other cases. So that case is just from the projection gives you an additional grading of the ring. So in this case, in case 2, we constructed as the mirror degeneration is this spec, or maybe it's rather a formal spectrum. No, this is a spectrum on a spectrum of some ring R hat. Okay, and that lives over some ring that I denote A hat. Yeah. So that's and in the case 1 of degenerations of Calabi-Yau, you get just a grading on the ring and approach. That is what that would not be proper. No, properness was imposed here, not here. This would be affine. Yes. And then sometimes you can argue that it's not quite the right model. It comes out with singular generic fibers. You have to do a little more. Okay, then, but let's first get something that is totally universal that we can start with. And of course, it's also related to constructions, ideas in symplectic geometry. This stuff is really something like the symplectic homology ring of the pair x, d. Okay. Okay, so let's start with the setup. Sorry, before I have a running example. As simple as it gets, but already, as you will see, highly non-trivial proof theoretical. It already features all the complications, essentially. So you take the blow up of P2 in one non-toric point. So you have 3 divisors. Let's call them upstairs D1. Let's get the labels right. D2, D3. And then over here, there's a D1 bar and so on. And that's the exceptional curve. So if that is sigma, let's just do the let's check this condition just for being. So if that is x, that's my x. So kx. Actually, did I want? No, that's kx, right? So I want sigma upper star kp2 plus e. So that's a minus d1 plus d2 plus d3 plus e, and then plus e. So this is minus d, yeah? Minus d1 plus minus d2 minus d3. So this is a really nice log Calabi-Yau case where kx plus d is trivial. So the ring will have generators having to do with contact orders.
Why even loop at all? Why not just take P2 with that and
You can do that too, but yeah, that in this case, let's see, gives probably the same thing. Okay. So I don't have a ton of experience with examples, and you can easily get me off balance by asking more and more questions on examples. Okay, let's see. So let's assume that, so of course I do assume that D has a deepest point, right? So D has also a 0-dimensional stratum. So P2, elliptic curve, one of my favorite examples otherwise, is not allowed. Okay, then we would have to first degenerate this elliptic curve. So XD, that comes with a log structure. Yep.
What mirror are you supposed to get?
What do you mean? What mirror you are supposed to? What do you mean?
What do you want?
Well, I told you. I mean, you think I should know what I should get an expectation? I think it should be the other way around, right? I have a universal construction, and then I can show you, okay, this is a mirror. Why should we have an expectation of what the mirror is? I mean, that's insane, right?
But you blew up, but you're using D1, D2, D3 and the proper transforms.
Yes. Yes, D is C, exactly, that's D, right? D is D1, yeah, I should have said this. Yep.
I mean, maybe one way to ask the kind of question that Vivek is asking, what properties do you expect your mirror to have? Like, there must be some desiderata.
No. I think it's the wrong question. We have a philosophy. Look. Mirror symmetry has a philosophy. It's telling you that we should get the mirror objects in a certain way, and that's what mirror objects in the sense of we have you think of Floer theory of intersection of Lagrangian sections. It comes from the SYZ philosophy. Okay. It's not a desiderata. It's how I start. So and then I produce a ring. So obviously the degeneration is an affine degeneration. That's how I wrote it down, right? Okay. I think it's bad science to ask either A, I have an expectation, or to ask I want the object to have the mirror object. We should ask the question, what is the explanation? What is the mechanism behind mirror symmetry, right?
The answer could be the empty state. That's a construction.
Okay, then go ahead. Then do something with it. That's a definition, right? That's a definition of a mirror. But I don't want a definition. We have a mirror mechanism. We have tons of examples. Okay, or you could say, okay, I don't have a definition, but when I see it, I know it is mirror symmetry. So let's go ahead. The SYZ philosophy fits with everything I know. Okay, and here's a construction of completely general offhand. Let's do this. Let's save this later. It's already 20 minutes into the talk, and I haven't really gotten to anything. Okay? I'm happy to talk to everybody in extent, but I would like to show you slightly of what the flavor is and why it took 3 years to write this paper. Okay? Okay, so that has a log structure. So, but a slightly friendlier answer. Okay, so the generators of my ring will be I would think of something like rep orbits. It's this zero part is a symplectic cohomology, and we're doing as an algebraic geometry version of that. Okay, so that will work for all pairs x, d. Hopefully, not quite true. If you don't impose conditions on D, you need the full symplectic cohomology ring, and then we don't really know what's going on. But these are the assumptions where we can prove that actually the ring closes up. Okay, and I think that's a very nice construction and fits well with all kinds of things you want to prove. Homological mirror symmetry, counts of curves, variations of hot structures, and so on. Yeah? Okay, so the log structure in this case can be written down very easily. It's a sheaf of monads. So these are the sheaf of functions having zeros at most along D. So if you have such a function that has vanishing orders, so that's a sheaf of vanishing orders, it's a discrete part of the log structure, also called the characteristic or ghost sheaf. It's mx bar. That's mx mod submonoid sheaf OX cross. So and if D is normal crossings, then this can be written down very easily, explicitly. It's just one copy of n for each irreducible component of D. Yeah? So these are the sheaf of vanishing orders of functions that have zeros along D. This records the vanishing orders. So from this, we can build the tropicalization. That works for any log scheme. It's based on the following observation. You should take, for each point x, we get a cone, sigma x, which is the dual, is a real cone. Okay. And then whenever y lies in the closure of x, that's a scheme theoretic point. So if y is or let's do the other way around, okay? If x is in the closure of y, then we have a generalization map, mx to my. It's a generalization map. And that's surjective. Okay? And then you get you get an inclusion, sigma y and sigma x, that turns out to be inclusion of a face. Face inclusion. It's another point, sorry. Yep. Yeah, so if you something like this, you would have had an n squared here, let's say P2, yeah, n here, 0 here. And of course, you get a generalization map in this direction, right? So in this case, you get a face inclusion, and the tropicalization is just the direct limit of all these things.
So when you write mx bar goes to y bar, you begin as mx comma x goes to mx comma y.
Yeah. Yep. Okay, so in our example, what would this be? We have 3 deepest points. Yeah? Maybe I should keep this over here, huh? We have 3 deepest points. Let's do it for the example. Let's do a slightly more interesting example. Let's not take D, but let's take D union E. Okay, so let's do the M bar or mx comma D union E. Okay, then what would you get? I have 4 cones, 4 maximal cones, 4 copies of n squared. And how are they being glued together? Well, the things that come from the divisor, the strict transform of the divisor forming the P2, that's just a fan of P2. But I'm trying to draw a three-dimensional picture because we have one more cone that has to do with this node connecting to the elliptic curve. Okay, so the whole thing won't be a manifold. There's another thing attached. So I mean, there's no ambient geometry. It's just a cell complex or a cone complex, a complex of cones, of real cones. Yeah, does it make sense? Okay, we don't need this component. Okay, let's throw it out. So that is the thing you have to deal with if you are in the D, NF, or anti-NF case. Then we also need to keep that component, and that causes trouble sometimes in closing up the ring. That's where symplectic cohomology produces other generators. But under the NF or anti-NF assumption or the log-Calabi-Yau case, we don't need it. So we go over to what is called the Kontsevich-Solomon or essential skeleton. And that depends on the choice of a logarithmic form, yeah, holomorphic end form. By just only keep those divisors, keep those rays, so the rays are the divisors, corresponding to those components where AI is 0. To DI with AI equals 0. So it's a stuff where your log form has simple poles. Okay? And that throws out that thing. Okay? So that gives a B in sigma x in this tropicalization. Sorry, huh? AI. Oh, the AI, I erased it, I'm sorry. We had this thing, kx plus d is numerically equivalent to some AI di. Yeah, that was in this assumption in the theorem. Sorry, I wanted to call it sigma x, not trop x. Okay, so that is then a topological manifold. But we don't need it. That's topological. Anyway, so that is this. And here, in this running example, we retrieve the fan of P2. So why do we want this? Well, I told you it has something to do with rep orbits. I take the integral points of B as recording vanishing orders of curves along the divisors. Or rather, not vanishing, that's bad. Contact orders of curves on D. Yeah, why is that? So let's do an easy example, right? So let's take just a copy of A2, that's the neighborhood of a node, and then let's look at a curve parameterized by T to A, T to B. Then if you tropicalize this, you get a map from the affine line with a 0 as a divisor to A2 with respect to this coordinate crosses, and you can work out the induced map of tropicalizations. That's covariant. And what you will see is that that point here corresponds, well, unfortunately the thing looks the same, right? But that's a dual space, and it will really give the point A comma B. Okay, so A comma B is a contact, means you want to count curves with contact of order A to the horizontal line, contact with order B with a vertical line. Okay? No, I'm saying each point of B tells you a bunch of contact orders. All the contact orders with all the divisors.
How does it tell you about the divisors that have nothing to do with that?
They're just zeros, disjoint, will be disjoint. So there's no condition on that, right? So it's just, so when you have a point here, there's a minimal cone containing all this. Let's say we are here, okay? There's a minimal cone containing this point. That will define the interior, that will define a stratum. So that would be, in this case, would be one of the divisors. okay? And then the integral point would tell you a contact order, specify a contact order with that point, okay?
So what is this point?
Sorry?
What about the origin?
The origin would be that makes perfectly sense. The origin is a thing corresponding to a big stratum, say x minus d stratum. That's a stratum. Well, there's no contact order, right? The only element in this monoid is 0. So you will see what it means, okay? It will mean you specify a point to run through. Right. Okay, so let's continue. So then we need a ground ring for a base ring for our degeneration, for mirror degeneration. Well, I call this, that's a P, some submonoid containing all the effective clauses and something that I call H2 of X. And I'm very liberal in what I mean by H2 of X. Take your favorite version of group recording classes of curves. Okay, that could be Chow, that could be H2XZ, singular homology. It could be, you could even choose to just take the area, okay, symplectic area. And P is a submonoid containing all effective classes, all curve classes. Could be a Novikov field or whatever. Novikov ring. But I want it up, and that's important. I want it finally generated. So you cannot always just take all the effective, you cannot take the effective cone that might not be finally generated, then you have to take a slightly bigger one. And of course the construction is kind of independent of this. If you make it bigger, you will just get open subsets and so on. Okay, so, and then to be precise, I have to cut off. So I want to take an ideal I. So that's a monomial, a monoid ideal, such that P minus I is finite. So that means that makes this ring Artinian, finite dimensionalized K-vector space. And then in the end, you take the limit. Okay, but to be finite in each step, you just cut off. Okay, not a big deal. So then you have the mirror algebra that will have one generator for each integral point. So it's an AI algebra. So it's called maybe RI. It's a direct sum AI, and then for each point, that's a little p. Okay, that's a capital P. Won't appear anymore. And there's one generator for each integral point of Z. And that should, if you do know of our theta functions, remind you of our theta functions, but here in the context of this talk, it's just a dummy variable. No. You will see that essentially all the game I'm playing happens entirely on D. Okay? But let's see what's going on. I mean, the most interesting part comes from actually D. So in symplectic homology, you should see lots of cylinders going around doing all kinds of things. Maybe you mean something different. There's
I'm asking why is it okay to have none
E. That depends on your choice of E. Yeah, yeah,
So this
yeah.
minus one comes from. The contribution started with 2 and I.
That's right. You would get that. You would see in this bigger ring. Yep. Oh, sorry, I misunderstood. Okay, so and then of course the whole point is that we need structure coefficients, right? So we want theta p1, theta p2 is sum alpha p1, p2 r, theta r, and that will be a finite sum, and because we are in this Artinian setup. And the theta r, and then of course the point is what is alpha p1, p2 r. These are the structure coefficients. They're given by counts n beta p1, p2 r times this t2 beta. Okay, so that's a class of beta, and I sum over beta and r. So and the n p1, p2 r beta. That's a count, a virtual count of curves, genus 0 curves, with contacts of orders P1, P2, and now you might expect I'm writing R, but I'm not writing R, I'm writing minus R. Okay, and you'll see why this is the right thing to do. P1, P2, and minus R. Yeah, with D. So
Is there a generator that corresponds to the complement of D with
yeah.
like a 0?
Yes.
That's the unit or something?
Yeah, yeah. That's just a unit. That's always in there, right? It's a cone thing. There's always a 0. That's a unit. Yeah. See it. Mm-hmm. Yep.
But it's not an augmented algebra. You can get a multiple of theta naught as by multiplying 2 other things together.
I don't understand this comment.
I mean, if I take theta p1 and theta p2,
Yeah.
like p1, p2 are not 0.
Yeah.
There could still be an alpha p2, p1, p2, 0.
Oh yeah, sure.
Okay.
Sure. There will be in many cases. So like say in the toric cases. Sorry? Yeah, I'll explain. I'll explain what this means. I mean, at the moment, it makes sense. I've told you contact orders, but I'm claiming that it also makes sense to talk about negative contact orders. Okay? Okay, so let's do just an example that's toric mirrors, because in this case, we get all the counts to be 0, except in the case where P1 plus P2 plus R is P1 plus P2 is R. So in this case, yeah, let's just sorry, I have right a toric mirror in the sense you start with X comma D is a toric variety. Yeah. Okay, and I want to get the Horry-Waffer. Yeah. So if that is non-zero, let's put it this way. In this case, it's 1 if P1 plus P2 is R. So P1 plus P2 minus R is 0, and it's 0 otherwise. That's actually already kind of difficult, not entirely trivial, to see from this curve counting point of view.
This is independent.
And beta is 0. Thanks. Sure. So that means that, so let's do an example, P1 cross P1. So that would be the mirror. I think that's my B. It's a fan of P1 cross P1. I have integral generators, let's call them X, Y, Z, W. So what I mean is, of course, X is a theta 1, 0, 1, and so on, right? That's how I should write this. And then you see that this is always 0, so I can draw tropical pictures, and they will always look like this. So this is my minus R, and then there will be a P1 and P2.
So your conditions allow, say, Hertzsprung surfaces, they allow F2, but they prohibit F3?
No. In the toric case, that's C1. The logarithmic cotangent bundle is trivial. They are all fine.
Do you have any quantum assumption? All divisors effective?
No, I told you, I wrote it down in the beginning. Kx plus d must be numerically equivalent to an effective divisor supported on d. So it includes all the cases where your Kx is linear equivalent to minus d, or minus Kx is linear equivalent to d, right?
So any toric?
Any toric. I mean, toric is a totally trivial case, yeah? So it already solved it here. Not quite. So what's the degeneration? The degeneration is a little more interesting. Let me do the completed thing right away. It's K of ST, so you have these formal deformation parameters, and then we have XY, ZW, modulo XY minus S, ZW minus T. This is A hat. Yeah, they have curves of by degree AB. That's the kind of thing. So quite generally in this toric case, we just retrieve what our program would spit out for working with empty wall structures. So the Ri is the ring of theta functions for empty wall structure. A slight question on the coefficient ring and so on, right? But it all works out nicely. So you have some universal, the numerical effective cone sits inside this dual of the Cartier divisors, which are piecewise linear functions on the fan and all this kind of thing, okay? But that works all out.
So here all you're saying is that if I invert S and T, it's a torus.
Oh yeah, sure, yes. That will be always the case in for toric varieties, yeah. So there's one interesting observation already. Unless we look at structure coefficients involving 0, the curves contributing to our sum all lie completely in D. Okay, this was what I meant when I tried to answer your question, Vivek. All curves contributing to n beta P1, P2R lie in D. Yeah, because we want positive contact orders with one of the divisors and then just completely in D. So for example, could be this kind of thing, right? So you could have some contact order with this one, some contact order with that one. But presume most of the time, right, unless P1, P2 are one of the EIs, it's just the contact orders live here somewhere on the edges. And then you look at curves, something they look presumably like this, okay? So this would be like, say, the P1, that's the P2, and that gives the R. That's the kind of curves we are counting. So they would map to this guy here. Yeah, so let me, now before I can continue, I have to say a little more on how to define these n beta R's. Well, precise. Some comments on the definition of n beta R, P1, P2R. So in log grammar-Witten theory, you just enhance all your curves with log structures. So you would have a curve, a space, and a parameter space, and they all come with log structures, okay? let's assume the base is just a 1 parameter family. Okay, A10, and I can draw some diagrams. You might want to think of base changing to the point, but then you get some log structure. This is very geometric if I just take an honest 1 parameter family. So what does this mean? Then locally, near a node, so we have some degeneration of, that's my curve, yeah, so that's my curve C. And then here's some parameter, let's call, I shouldn't call it T now, right? Maybe a little W or something. So that's my curve. And then there's some marked point. Unfortunately also written X now. It's a family of marked points. And you have some C0 and a map to X, capital X. Now, if you pull back, let's say X is also very simple. It's just an A1 with divisor point. Yeah, so or a smooth divisor. Okay, let's take a smooth divisor. So that has a generator that lives in the log structure MX. Okay, and you can pull back. So if you pull back this equation, let's say this is Z equals 0, then you can pull back, and what you will find is, so the log structure on this curve is induced by what you see, yeah, by this nodal curve. So there is something happening at the center fiber and something happening at the marked point. So the pullback of Z must have zeros on this X locus and on C0. Yeah? That must be contained in C0 union graph of X. And that means that if you look in the log structure here, so the map of log structures that you obtain here, so let's take this point here, that's the interesting point. Yeah? Let's call it P maybe, and this is f of P. So then we have a map M bar X f of P, and that pulls back with the corresponding map F to M bar C P. Now this is an n squared, this is an n. Yeah, the vanishing orders. It's the n, the vanishing orders of functions here. It's the vanishing orders on two functions. So that will map to some, the generator here will map to some AB, just as we saw before, with this cuspidal curve. So what's the contact order? The contact order, so the A here, oh, there's one generator coming from that guy, right? Let's say this is the first one. So let's also say there is this M bar W 0, and let's say this 1 maps to 1, 0. Okay, then the contact order that you record, the contact order of the curve with at point with the divisor D is given by the second factor with the B. So what I want to tell you is that in this, at a special point of the curve, as a marked point, you get a copy of this log structure from the base. That's our first factor in this n squared. And then you have a projection to the second factor. So here's this AB is in there. And that gives you, that tells you the contact order. That's B. And obviously, from the way it's written, it has to be positive or non-negative. So how would we change this whole thing to include negative contact orders? That's the whole point, leading to the theory of punctured curves. So that's work with Sheila Chen and Dan Abramovich in progress. Also another companion paper coming out, hopefully also this summer, who knows. So painful to work. For 4 co-authors paper, I mean, that's difficult to organize, right? I don't know what your experience is. But it has been a good collaboration. Just hard to get things finished. Okay, so what is this? So you have to enlarge your M. That's the point. So you have the MC. So that looks like, let's say Q, let's say n squared. That's the n coming from the base, and another n. And you view this as a submonad of a puncturing which sits inside n direct sum Z, but is finitely generated. So what's going on is you have this monad, and you embed it by allowing negative contact orders. So you enlarge this kind of thing, get this. So if this like the X order, it's actually the other way around. Anyway, I swapped the A and B. So that would be B comma A. Yeah? And now I allow negative contact orders. And the M, everything, so as long as I'm staying in the upper half plane, all the additional monomials that I put here, all the additional generators, map to 0 under the structure map. So that's legal. Okay? I should not go here. Then I have no structure morphism to OX anymore. But think of these as something like, that's like an X to B, T to A, okay? That's a function in, here we have a T, here we have an X. Too many X's here, too bad. Let me call this, I don't know, that's a P or what. Yeah, that's a function on that, near that node. Okay, so T records the deformation direction, X along the curve. Negative contact order means taking negative powers of B, and what I'm saying is, if I take negative powers of B, the power of A, the power of T should be positive. So this just maps to 0. It's just something entirely virtual going on, having to do with line bundles, rather than with actual functions. And with this simple definition, everything goes through. I mean, the modifications to log-Gromov-Witten theory are minimal. It's just very confusing to work with these things, okay? But the definition is essentially the same. You just copy-paste what you have already done. Yeah, so this gives log-Gromov-Witten theory. Sorry, punctured Gromov-Witten theory. So now I have to, the n beta P1, P2 are just log Gromov-Witten invariants. For symplectic geometries, there's no sweat, I guess. You just have your orientations of the Reppe orbits. You don't care if it's positive or negative, right? Do you? Maybe you do. But you can formally make this definition. For algebraic geometries, it's a little more confusing. Okay. So and then you define so you have the virtual dimension. Oh, I should say the following. So you get a moduli space, unfortunately also M, written M, M X beta. Let's abbreviate. So beta now contains beta underlined and all these P1, P2 are. Okay. And we have a map from mx beta. Now there's one thing. The dimension is not quite right. If you try to do it, you can do it very naively. You just fix 3 contact orders, 1 negative. You go too high dimension. It's not 0 dimensional. What you should fix is 1 outgoing point. Yeah, so you have to fix 1 point. But still not quite right. You have to fix it logarithmically because the outgoing point comes with a line bundle having to do with the normal bundle of your curve. So you fix that, it's a framing in symplectic geometry.
So the normal bundle of your curve is the normal bundle of the markup in the curve?
Yeah, think of this map, right? So think of MC.
Elementary question. The normal bundle of what and what?
There are two normal bundles, and they are related. So you have the normal bundle in X of the divisor. And that pulls back, that gives you a certain, that pulls back to something on MC. When MC has stuff that is trivial, it comes from the base, and the other stuff at the mark point is a normal bundle of the mark point inside the curve.
Yes.
Okay, and they are related, right? So that maps, they have to be, so that's the...
If you say I fix an arbitrary output point, that could in principle not lie in the divisor, on the divisor.
Oh, we fix R, okay? R, so we want to define n beta p1, p2, R. So R is fixed. R tells you a stratum.
Okay.
So that gives you one of the points, and that fixes the things, okay? So the Z is Z is in R stratum, or interior of R stratum, fixed, arbitrary, yeah? And then plus fixed normal bundle, fixed bundle, logarithmically. Okay, and that has virtual dimension equals C1 of X times beta. And that's the logarithmic C1. Okay. So in your Calabi-Yau case, toric, let's say with toric boundary, that is just always 0 for any beat. And then you define the n beta p1, p2, r as this as a count, yeah, as a Gromov-Witten invariance. So that's the degree. That's the degree of this modelized space M of x beta z. If z is 0, if c1 x times beta is 0, and it's 0 otherwise. Okay. Tropically, well, let's see. I have like 5 minutes left. So tropically, I'm drawing these things. So tropically, I'm getting tropical curves. Well, a kind of relaxed notion of tropical curves. So if this is our example, that is a B in the example, you would get, I get vertices, they correspond to the irreducible components. And then I get edges. And I get outgoing things, they correspond to these PIs. Something like this. And then I might want to also, then the R will be denoted, so that's just so the PIs are in the cone, yeah? So they are in the cone. So they cannot point down or something, right? There's an infinite ray. They lie in these cones, but the R lies just in the group, in the R times sigma. Okay, so they can point to the origin, for example, and that's what we'll do, yeah? So they will actually always just point, so saying Z in the interior of the stratum means it actually just points to the origin. So these are the tropical pictures. So I don't have really time to tell anything or go through the example. Well, I should at least write down the formula, okay? So what do we get in the running example? The result is, in running example, so what's the mirror we are getting? And then you can argue if that's the mirror that makes you happy, but in terms of expectations. So the mirror we are getting by this construction is AI of theta v1. I should give these notions. So the vi's are ideal to these divisors, and I lost my, so that was the v3, I think. No, that's v1 actually. That was the v2, and that's the v3. So we have theta v1, theta v2, theta v3. Oh, the central fiber, actually, that's always just given by what you see torically. So you get a bunch of copies of AN coming from the nodes, and you glue them together as you see, okay? And that is your central fiber, okay? So that's always the degenerate kind of the N vertex, the union of FANs. In this case, you just have 3 copies of A2. They would be given by this theta V1, theta V2, theta V3. And it's a flat deformation. Yeah, I didn't state this. It's always a flat family, of course. So you only have to deform this equation, and you get a T to L. L is a strict transform of the line. And then T to L minus E theta V1. Okay? So that's the result. I plan to explain you these coefficients, but I don't have time. Happy to show you afterwards. So L is a strict transform of the line, yeah? That's E, and L is just strict transform of the line. So just orally, what is the thing about the proof? So the proof is, as you know, the point is proving associativity, okay? So how do you prove associativity in Gromov-Witten theory and quantum cohomology? You look at a moduli space of 4-pointed G and 0 curves, and then you do your business with looking at the 2 special points that you obtain from this 4-vertex tree to either this one or that one. Yeah? We do much the same thing, except everything is a lot harder and more subtle. The reason is that this moduli space, so you look at your moduli space M, X, beta, Z. Well, now you have an additional point. So we have 4 points, X1 to X4 or X out, and then beta, okay? And you want to show it degenerates nicely. Now, if you look at the tropical picture, that's what I try to indicate here, you get something generically. The generic picture, so in the interior of the moduli space, it looks like this thing here. That's a generic picture. Yeah? So that has a 4-valent vertex. Then we have, that's another vertex. There are 3 irreducible components. That's the interior thing. So then you go to the boundary. You degenerate to one of those situations, growing an edge, meaning growing a node, an additional node. And that comes in here. That's the limit. But this is not where you can compare with the individual components. That has nothing to do with any individual components. You want to split this into 2 diagrams that look very similar to the ones you started off with these 3 kind of things. Yeah? Just doesn't work. So then there's an additional parameter that you only see logarithmically that you can crank up or play with. The point is there are 2 intrinsic things here. The one is this, oops, that's not a good color. Is that length here. That is intrinsic. And then there's the length of the edge connecting the x1, x2 thing to the x3, x out thing. That is that edge, okay? That has another length. You need this length to be very large compared to that one, okay? So there's a kind of wall crossing, but hopefully you have to show it's independent. It's an invariant. So what this does is it goes through a borderline case where you shrink that edge. That's still not good. And then you go then you crank up L. And then you get 2 pictures actually, 2 tropical pictures, where you have a unique edge, not a tree of edges, but a unique edge that you can split. And then the splitting is hard. Again, because you have to show that the work with Dan in Chile that we have worked for so many years very hard, and that we still can do in complete generality, but we can do enough to solve that case. Okay, thanks for your attention. In this case. Well, or for degenerations you get projective, yes.
Right, but even in this case, with the one caveat, you get something outline. You could ask, once you have this, to match up the variance on either side. So far as I understand, on the side with the one caveat, morally you're trying to understand something about like a rat who had a greater complement. Is this right? So on the other side, I'm surprised. What are you going to say about compactifying the outline that you get? Like any coherent sheath over there with proper support is supported at some number of points, right?
We understand that question pretty well, actually. It has to do with the fact that the D has nodes. Okay, the D has deepest points. So the fact that the superpotential is proper is equivalent, or not sure how general I wanted the statement to make, but it should always be equivalent to the divisor being smooth. Okay, so what you would have to control is you have to play with this picture in understanding what's happening under smoothing the nodes. And that will introduce some kind of compactification. Yeah. So I maintain this a base case, like dealing with the most affine, or most singular things. And then you may want to further degenerate corresponding to some birational game and so on.
So for you, the mirror is the zero locus of the superpotential?
Say it again?
For you, what you call the mirror is the zero locus of the superpotential?
No. No, there's no superpotential. I could tell you what the superpotential would be the sum of the theta VI's.
What is the mirror? Oh, I see.
Yeah?
So for example, the mirror one in your construction would be something like C star.
The generic fiber of the mirror. That's not the mirror. I mean, the whole family is a mirror.
Okay. And then the superpotential on that would be the usual thing?
Would be in the toric king, it's a Hori-Waffer thing, yes.
So can you explain again how those deformation parameters arise?
These are the curve classes, right? The T to L, that's a decoration. If you remember, I wrote down the product, the theta. I had this formula, right? So it's something like theta.
It's more or less intersection of the curve with boundary divisors.
Yeah, it counts the contact orders. Well, no, it's not. No, that's the curve classes, right? It's the curve classes.
It's a curve class measured by.
No, that's an element of the base ring. It's a universal thing that counts, that carries these things. It's not just a number. It's a base ring. Just as in Gross-Hacking Kiel, you have a base ring, the numerically, or something that is close to the numerically effective cone on the mirror side, on the side you started with. Again, for P1 cross P1, it's the numerically effective cone is n squared by degree, right? And so I have two deformation parameters, S and T. But that has a priori not, yeah, you could argue it's given by intersection theory, yes. If that makes you happier.